there's another type that we'll deal with after this called optimization. But both are applications of the derivative to some extent. And yeah, so we're going to dive right in. Now, the process, I mean, it's pretty, in some ways, pretty vague and unhelpful. But in other cases or other areas, it's pretty useful. Like draw a diagram, may or may not be helpful. Determine which quantities and rates are given and which to be found, pretty helpful. All right, identify the primary function to use. Often this is a formula from geometry, pretty helpful. Differentiate with respect to the independent variable, not very helpful, because that depends. I mean, you had to figure it in calculus. At some point, you're going to take a derivative along the way. That doesn't tell you whether it's going to be an easy problem or a hard problem. Right? So, okay, I'll have to take a derivative, but that might be the most tricky part of the process. Number 5, step 5, write a related rates equation. That just seems like, wow, we're finally getting around to that. But a related rates equation is an equation that relates, which is what an equation is. It's a relationship between variables. What we're saying is we want that relationship to be between rates of change, right? So it's the process of differentiating that leads us to the related rates equation. So if you differentiate correctly, then this next part will naturally occur. All right, this will be a natural consequence. All right. So step 5 is a consequence of step 4. All right. Step 6 is that's the home stretch. That's like, all right, now plug in some numbers and get an answer. So that part we're not really too worried about. I would even amend that last one to say, and don't forget to incorporate appropriate units, right? Anytime you're dealing with word problems, we need appropriate units. Yeah. All right, so folks who just checked in on the chat, I have you for attendance, so you're good. So there's a few different varieties of related rates problems. One is, I mean, it almost doesn't matter what you call them as long as you kind of recognize them when you see them, in the sense that when you look at a word problem and pull out relevant information, you know where that information belongs. Right? But it takes some time to get a handle on. But that's what I'm here for. So air is being blown into a sphere at a rate of 6 cubic inches per minute. How fast is the radius changing when the radius of the sphere is 2 inches? And it's like, all right, I guess I could draw a sphere. I mean, I personally can't, but I could throw a sphere in there. I don't know that it's actually going to be too helpful to do that. I could show you an app that could be useful. It's called Geogebra. So geogebra.org and then /3D. It's not, I mean, they don't really have an app. It's just their website. It has a little bit of a similar kind of feel to Desmos, except it does more with three-dimensional math. Now, when you get to higher levels of calculus, you'll really see the power of something like this. But I mean, if you needed to sketch out a sphere, I mean, you could also go to Google Images. They don't really need to make things too crazy. But the equation of a sphere centered at 0, 0 is x squared plus y squared plus z squared equals whatever the radius is. So this one doesn't, oh, it does tell us that the radius will be eventually 2 inches. So I could throw in a 2 squared. So it's the same structure as a circular equation, just you throw in a z squared instead of just x squared plus y squared. But it's not like it's required knowledge for the course. It's just if you're interested in knowing how to make a sphere using some technology, this could be the way to do it. All right. So I'll do that. I'll just grab this and here, I'll take a little screenshot of it, make it a little smaller. And I'll just pop it in there. I'm just trying to get a good orientation. Oh, you can animate it, by the way, in case you're wondering. Looks great. When I teach my Calc 3 classes, this app is kind of like where we live, because it's hard to really illustrate and evaluate omnidimensional mathematics with just pencil and paper. Some people are good at it. I'm not one of them. So yeah, but like I said, it's not part of the course to create three-dimensional figures. So this is just fun fact of the day territory. You don't even have to draw an image because most people know what a sphere looks like. I figured I'd kind of give you a little taste of that. Yeah. So they're telling us a rate of change. They say air is being blown into the sphere at a rate of 6 cubic inches per minute. All right, I'm going to write that down. 6 cubic inches per minute. All right. Just focusing on the cubic inches, that's a measure of volume. All right, so it's a measure of volume. The minutes, I think that's probably pretty obvious, goes without saying, that's a measure of time. All right. Now this rate that they're telling us, they're not indicating that this is happening over an interval. They're saying that this is the rate of change at any moment in time. All right. So what they're implying here is that this is an instantaneous rate at any moment in time. All right. The key word there being instantaneous. Now, they can't really write it like that. They can't say air is being blown into the sphere at an instantaneous rate at any moment in time of 6 cubic meters per minute. How fast is the radius changing when the radius of the sphere is and really how fast is the instantaneous rate of change of, or how fast is the instantaneous radius changing when at any moment in time the radius is, it gets a little too wordy, is what I'm getting at here. But bottom line is, since this is a rate of change and it's instantaneous, this must be a derivative, right? So this must be, for lack of better variables, dv dt. The instantaneous change in volume per instantaneous change in time. All right. So here I'm saying we're going to let V equal volume in cubic inches, and we're going to let T equal time in minutes. But I think my arrows and the circles and underlining and stuff like that kind of gets that across. So that's telling us that dV dt has to be 6 cubic inches per minute. Now it's asking how fast is the radius changing? All right, so I guess we'll let R be radius. All right, so how fast is it changing per what? I mean, if you're talking about a rate of change, it's change in one variable per unit of change in the other. It seems like the relevant variable that we're comparing to would be time. And how fast is the radius changing per unit of time? I mean, it seems to make sense. So it's asking us, what is dr dt? And the key word there is fast. How fast? That's an indication of speed. Speed has a component involving time. All right. So what is speed except distance over time? All right. So the radius here is serving the purpose of distance, and t is obviously time. All right. So it's asking us to figure out what dr dt would be when the radius of the sphere is equal to 2 inches. All right. That's probably the only part. I mean, when you're first getting a handle on this stuff, that's probably the only part that makes immediate sense. All right, they're telling us, okay, the R for radius is going to be 2 inches. All right, I got you there. You know, everything else is like, all right, we got to pull it. It's almost like we're pulling it from the problem, kicking and screaming. All right. But what's happening here is you have airflow. All right, so you have a source of airflow that's being projected into the sphere in some capacity. And what that's going to do is it's going to increase the radius of the sphere. I mean, it'll also increase the diameter of the sphere. And in turn, increase the volume of the sphere. All right. However, they're giving us a sense of how the volume is changing. They're saying air is being blown into a sphere at the rate of 6 cubic inches per minute. It doesn't matter what form that air was in previously. It's still being blown in at a rate of 6 cubic inches per minute. The volume is volume no matter what the shape of the volume is. It could be in the shape of a cube. It could be in the shape of a sphere. It could be in the shape of a pyramid. Volume is still cubic something per, if you're talking about a rate, per unit of time. Okay? So there's some source that's blowing the air into the sphere, and it's increasing the size. I mean, the obvious example would be like a beach ball or something like that. But you know, that's kind of a tricky example because you don't start off with a full perfect sphere and then increase its radius from there. You know, when you're dealing with a beach ball, usually start off with something that's, this like flabby little thing that's just kind of floating out there. And then as you put the air in it, it starts taking shape and eventually it becomes a sphere. Right. So it's a completely, formless figure until it becomes the geometric shape. As an analogy, it sort of falls flat, but it's the best we can really kind of consider, because balloons aren't good examples either, because those are hardly ever spherical. But anyway, we have a volume formula when it comes to spheres. Volume of a sphere V is equal to 4/3 pi times the radius cubed. All right. Old school formula from geometry. All right. We run into a little bit of a problem when it comes to geometry formulas, and that is, to the best of my knowledge, geometry is not a prerequisite for anything. But in theory, you've come across this formula along the way. If not, here it is. This is the volume of the sphere, 4/3 pi times the radius cubed. All right. What we have to do, we drew the diagram. We didn't really need the diagram, but we drew it anyway. Identify the primary function to use. Done. Often it's a formula from geometry. Yeah. Well, it's funny how that turns out. Differentiate with respect to the independent variable. That's the step where it's like, all right, I mean, that might mean something as long as you know what the independent variable is. All right. So it's a question of what are we taking derivatives with respect to? Not x. Here I'm looking at two derivatives, dv dt and dr dt, that are both represented with denominators dt. So what that's telling me is take the derivative of both sides of this equation with respect to time. All right, so I'm going to take the derivative with respect to time, again, of both sides of the equation, right? Because taking a derivative really is a property of equality. You're allowed to do it to both sides of the equation. All right, so I'm going to take the derivative of the left side, which is v, and separately, I'm going to take the derivative of the right side, which is 4/3 pi r cubed. Now, you might remember from implicit differentiation, there were some strategies that we talked about in terms of just getting the answer, but then there's the theory behind it. So the theory was we would always apply the chain rule, assuming that whatever variable was in the function could be also a function of another variable, right? So what we would have to do here, and I'm actually going to be explicit about this, is we're going to assume that volume and radius are also functions of time. I didn't want to hit copy. Hang it, resize. All right, so we will assume volume and radius are functions of time. All right, and what that means is that the volume will change depending on the moment in time, and so will the radius. And I think that makes sense. If you're visualizing this balloon or the sphere expanding, well, the volume would expand. It's going to get bigger or smaller. I mean, it's in this case getting bigger. All right, but that would, depending on the moment in time, it's going to be a different size. Corresponding to that would be that the radius itself would be changing based on the moment in time, right? So what we're actually saying here is that v can be thought of as v of t, and r can be thought of as r of t. The issue here is we don't know what those functions are, right? We have no idea what those functions are, but we could still differentiate, right, numerically to some extent. So what we would do is we would treat this like any other problem, you know, like pretend all our variables are x's. What would you get if you took the derivative? I'm looking at a 1v to the first power. All right, it would become 1v to the 0th power. But then by chain rule, I have to take the derivative of my inner function. My inner function, v, is really v of t. Right, that v of t, I can represent its derivative a couple of different ways. One way would be to throw a prime on it. A lot of folks like writing it this way because it's a little bit more concise. You could say v prime of t. But we also know, you know, like f prime of x, y prime of x, whatever. All those forms of notation, they all just mean dy dx. This just means dv dt. The 1v to the 0th is just 1, so that's irrelevant, right? But you could also kind of, I mean, aside from actually computing the derivative, you could also sort of talk your way through it, because you're saying, all right, well, what is the derivative of v with respect to t? The derivative of v with respect to t would be dv dt, right? The derivative of the function v with respect to t, right? So you could do it that way also, but This way is a little, I mean, in terms of getting the concept across, this way is a little bit nicer. The other way is a little bit more efficient, right? I'm just going to smidge this over a little bit. Now for the other piece, derivative with respect to time of some function involving, or a function involving some function R. All right, so differentiating that, and get purple involved here, power rule, 3 multiplied by 4/3 is going to give you a 4. Pi r squared, but we also have to be mindful of the fact that r itself is a function of time. The derivative of r can be thought of as r prime of t. Could also be thought of as dr dt. Right? Do we have to write it both ways? No. However, we're looking at a problem here where we've just identified a dv dt, and we've established that we're looking for a dr dt. So it kind of makes sense to write it as dv dt and dr dt. All right. But this is what we call a related rates equation. All right, because it's a relation related of derivatives. Those derivatives are instantaneous rates. So we are relating rates to one another. All right. So at this point, all the hard work is over. It's just a matter of plugging and chugging away. Because they told us that dv dt was equal to 6 cubic inches per minute, so 6, 4 pi r squared. Sorry, we actually know r. They told us r was 2 times our unknown dr dt. Once we go through this process, we'll have our answer, the process being actually solving, but the work is done, because 4 times 2 squared is going to give you 16. So 6 over 16 pi, that's going to be 3 over 8 pi. All right. We do need units. There's 2 ways to come up with the units. One is involving just plain old good old-fashioned intuition. So if you don't have any of that, you'll need another method. All right. The other method is to go by the actual units in the problem. All right. So I'll take you through the units in a second, but if we know that I'll take you through the derivatives, a method for finding the units. They told us that the radius was measured in inches. We're looking for radius per unit of time, right? Radius is inches, unit of time is minutes, so inches per minute. All right, so it's just looking at the notation and just recognizing, well, radius is linear measurement. What are the linear measures? It's in this case, it's inches. And so there you go. So 3 over 8 pi, 3 over 8 pi inches per minute. All right. But let me just show you really quickly, not too quick, but let me show you how you might come across or come up with the units through the derivative process. Even if it's not something that you anticipate yourself doing, it's definitely worth kind of tuning in for, because it's kind of the beginning of the understanding of where a lot of the units that you learn in maybe a science or specifically a physics class actually come from. All right. So when we started off with this notation here, or this formula, we had volume in cubic inches. So I'm going to throw in all the units here. We had R in inches. Right. When we went through the derivative process, we came up with this. All right. But really, what we came up with was a little bit more than that, because that V here, that's V inches cubed. And over here on the right-hand side, this R squared is really R inches squared. And this R over here is R inches. All right. Based off of our discussions involving the problem itself, we noticed that time was measured in minutes. So we can just kind of tuck that in there, T minutes. So when we go through the solution part of this, the units come along for the ride, right? So we would say dV cubic inches over dt minutes. We would have 4 pi times 4, I believe it was 2 inches squared times dr inches dt minutes. So all I'm doing here is exactly what I did before. It's just I'm bringing the units along for the journey. All right. So I have dV inches cubed over dt minutes. We'd have 16 pi inches squared times dr inches dt minutes. All right. Now, when you go through the process of actually solving, we divide, or when we went through the process of solving, we actually substituted in the measure for dV dt. So I could do that in the next step. That was 6 inches cubed per minute. All right. So the dV dt gets swapped out for the 6. We have 16 pi inches squared. The RDT, I could write it as inches per minute based on rules of multiplying fractions. I mean, you put them together, you can take them apart. All right, but when I go to solve here, I would divide both sides by 16 pi inches squared. Inches squared divided into inches cubed gives a result of inches. So 6 over 16 gives 3 over 8. So 3 over 8 pi. The units themselves actually simplify down to inches per minute. And on the right-hand side, so this cancels, dr dt, inches per minute. Right, so it's creating a proportion with consistent unit relationships. Right, all because we kept the units along for the ride, but it's very, very tedious to keep writing the units every step of the way. We clearly and obviously don't want to have to do that every single time, but we do it the one time so that we can learn, right, this really is a thing, and then we never have to do it again, right? But that's a little bit of a justification to explain to you that the units, they don't just come out of thin air, right? In fact, if you're anything like me, you probably kind of get annoyed when units do come out of thin air. You know, like I always got really aggravated, especially in physics, when we would solve a problem and I would put down, all right, 32 newtons. And then they'd be like, no, that one's pounds. Like, oh, crap. All right. And then I go to the next problem. I'd be like 32 pounds. I'd be like, no, that one's units. I'm sorry, newtons. They're like, I don't know what's going on here. Like, where are the newtons coming from? And then I was like, well, what the hell is a newton? You know, it's like the idea that you can just measure something and call it your last name. Like, I'd like to have some kind of understanding of what the hell a unit, the Newton unit is, you know, but it actually comes from calculus, which makes sense because Isaac Newton, calculus, and so on. But you know, kilograms, meters per second squared, I think it's something like that. Yeah, I think it's F equals ma. So yeah, kilograms for the mass and meters per second squared for the acceleration. So kilogram meters per second squared. You get those units, and then along the way, it's like, I would just call that a Newton. I'm like, oh, okay, well, I actually like the other form better because it tells me a little bit more about what the hell is going on, you know? So that's why I do stuff like this. I show you the genesis of the unit relationship because I personally find it incredibly aggravating when units seem to come out of thin air, right? So if you're in any form like I am, maybe you appreciate it. I don't know. We'll see. Right. But that's our solution, 3/8 pi, right? Inches per minute. Number two, and you know, like I made that a lot more complicated than it needed to be because the actual solution is take the derivative, throw some numbers in and get an answer. But I've taught it that way before. And what happens is I go through a bunch of examples in class and then people go home and they don't know how to do any of these problems on their own. Right. So if I'm droning on because, you know, for one problem, it's because I want you to try to understand conceptually what's happening here. Right. Number two, I might actually be able to draw this one somewhat okay, I suppose. The edge of a cube is increasing at a rate of 2 inches per minute. At the instant the edge is 3 inches, how fast is the volume increasing? So I'll just draw a cube real quick. It's not going to be pretty. Because I gotta kind of take a construction approach because I don't know what the right term is, but judging distances is not one of my strengths. Like depth perception, I guess maybe. It's not really good. I'm not really good. Okay, well that's not a cube. All right, that's the best I can do. All right, now I'm using an app to help me with that. So I mean, you can only imagine how disastrous that would be if I wasn't using an app. And it's not even like a perfect cube, but it'll get the job. All right, so the edge of a cube. Now, it only addresses one edge because all edges in a cube have the same length. So if one edge is going to increase, then they're all going to increase. Because in order to maintain the geometric figure of a cube, they would all have to simultaneously increase at the same rate. All right, so what I would do is define the edge. Of course, we would let S equal the edge, right? Because E, I mean, I say of course, but maybe it's not obvious. We tend to stay away from defining a variable using the letter E just because it's Euler's number. And so if you try to use E in technology, it thinks you're talking about 2.718. So we tend to stay away from E. S for side. So side and edge are analogous, I guess. The edge is increasing at a rate of 2 inches per minute. 2 inches per minute. All right. So the units on top tell me that we're dealing with a linear measure. The length of an edge, we'll even throw the word length in there, that seems to be a linear measurement, linear as in inches, feet, miles, things like that. So I could say ds to address the numerator, t for time, so dt for unit of change in time, it's increasing. Increasing would be a positive value. It hasn't come up yet, but if something were decreasing, if the rate was decreasing, well, actually not even the rate, but if the length or the volume or something like that was decreasing, then the rate itself would be negative. Okay, so in this case, it's positive. Now, it says at the instant the edge is 3 inches. All right, so at some point in this whole journey, overused word of the century, the length of the side or edge is going to be 3 inches. It's not always going to be 3 inches. It's not constant, but there will come a moment in time in which it's 3 inches. We want to know how fast the volume is increasing. So when S is equal to 3 inches, what is the rate of change of volume? The rate of change of volume with respect to time, right? Because the volume is increasing according to the length of the side, which in turn is increasing according to changes in time, all right? So it's asking what is dV dt, all right? So I need a formula, and it's still geometry, geometric situation. I need a formula that's going to relate volume and the length of a side of a cube, all right? So volume of a cube seems to be what the doctor ordered. All right, so V equals S cubed, using the variables that we're working with in this case. We're going to take the derivative of both sides of this equation with respect to time. All right, so we don't want to reinvent the wheel too much. I mean, dV dt is going to be dV dt just like it was in the last problem. Here we have to assume, just like we did in the last one, assume V and R are functions of time. V and S are going to be functions of time because depending on the moment in time, this cube is going to have differing volumes. It's going to have differing lengths in its edge or in its side. So there is an inner function S. That function S is defined in terms of time. So S cubed would have a derivative of 3s squared, but then I would multiply by s prime or ds dt. I choose to write ds dt because that's the notation I used up here. All right. They're asking us for dV dt. So I plug into the right side of the equation. S is equal to 3 inches. I'm going to throw the little units in there. ds dt is 2 inches per minute. So I'm looking at 9 inches squared times 2 inches per minute. And you see how the units work out here? Actually pretty cool if you think about it. It's almost like this problem is how the units for volume were invented, you know, something along these lines. Because if I take 9 inches squared and multiply it by 2 inches, I get 18 inches cubed, which is the measurement for volume, right? Unit of measure for volume. The rate is per unit of change in minutes. And so 18 cubic inches per minute is what my, oh, sorry, I put the wrong, oh, wait, whoa. The heck was that? No, I think I put everything right. I saw the 2 up here and I was like, oh, I put the wrong number in here, but I didn't. That's fine. So 18 cubic inches per minute. I don't know what that error message was though, and it's terrifying. I would know what that error message was if I actually read it, which is probably an issue. I should probably do that every once and again. Maybe I wouldn't have to retype my notes all the time when my computer and other devices crash. So anyway, those are some geometric cases. You know, it's a matter of identifying a formula, taking the derivative. And, you know, we were talking about this before. What ends up happening is you either get this concept of implicit differentiation or you don't, conceptually, you know, the theoretical. If you do, then you're good. If you don't, then you take the derivative and slap on a dv dt, slap on the ds dt at the end. You don't know why just yet, but eventually, like I said last time, it clicks. You understand it clicks at different moments for different people, but when it does, you'll be good. It just, I mean, I can explain it 100 different ways, but oh, gotcha. All right, so as long as I don't delete this file, I'll be good. Yeah, I could explain it over and over and over again, but it's all going to be the same explanation with slightly different terminology, right? So it's just a matter of like you consider it, you ponder it, you think it over, and then one day you're just sitting there looking up, and you're like, why didn't I see it before? So it'll happen. It always does. It's just different moments for different folks. Now, number 3, we start bringing this into the world of functions. A point moves along the curve y equals x minus 3 squared. Parabola, such that its x coordinate is increasing at a rate of 4 units per second. All right, so well, I can actually plot an x coordinate on here, a moving x coordinate. I mean, you can too. It's just a matter of defining it. All right. So instead of calling this y equals, I'll call it f of x equals, so I can evaluate the function. I'm going to create a point. That point is going to be a, comma, f of a. Just evaluating a function, create the slider, and then you'll have a moving point along your graph. Right? Because you're allowing a to take on any of the values here between -10 and 10. We don't even really need -10 to 10, even like 0 to 6. That would be fine, you know, just so it doesn't go running away on you too much. You know, so something like this, you know, something like that. You know, go a little higher so it looks like it goes off the grid a little bit. And, you know, just go ahead and animate it. You see it's on the move there. So that's what's happening here. Now it's saying that the x coordinate is increasing at a rate of 4 units per second. If I ever figure out how to make the point move at a certain rate, I'll let you know. I mean, I know you can make it go twice as fast or whatever, but 4 units per second, I mean, that's oddly specific. But it's saying at the moment that x is equal to 1, how fast is the y coordinate changing? So at this location, all right, so I'll actually plot that point as a separate coordinate, 1 comma f of 1. All right, I'll animate this. This coordinate is moving around. It's going to come downhill in a sec. When it passes that purple point on the way down, right? Because on the way down corresponds to on the way to the right. It's moving past that point at some speed. What this question's asking us is to determine what that speed is at that moment, right? So it's going to come down at some kind of speed, assuming that the computer doesn't lag, but of course it is. We just need to figure out what that speed is, right? How fast is the y coordinate changing, right? How fast is it going down as it's going to the right, right? Because we know it's going down, we can see it going down, How fast is it going down? Not how fast is it traveling along the path. How fast is it physically going down? Right? Down as in straight down. Right? The vertical component of that vector. Right? So that's what we're going to figure out. So we're given an explicit function here, which is nice. Y equals, it's for a change, we don't actually have to create a function on our own. Y equals x minus 3 squared. Now, if I differentiate this, I could take the derivative right now. I would be taking the derivative of both sides of the equation, not with respect to x, but with respect to time. Right? This is the beginning of what's known as parametrics. It's parameterizing an equation. It's introducing an additional element, an additional variable, and this variable in this case is time. Right? So on the left side, I'd have dy dt. On the right side, again, we're assuming that x is itself a function of time. Right? In theory, and actually not even in theory, in an ideal world, you would have learned about parametric equations in Precalc. The issue is that it's one of the optional topics. So what happens is when people run out of time, they start chopping off the curriculum. But in anticipation of the fact that we always run out of time in Precalc, most people say, "Oh, optional topic, I opt out." Right? So it's possible that you never saw it. Right? The next time you will see it would be in the beginning of Calc 3. But bottom line is we can write y as a function of time. So y is a function of time. X is also a function of time. All right? Because x moves at a rate that's independent from the rate at which y moves. We don't know either. Well, we know what x coordinate is increasing at 4 units per minute, 4 units per second. All right, so we do know one of the rates, but we don't know what function actually gives us that rate. I mean, assuming that it's actually a variable function. I mean, it could be a constant function, in which case it's always 4 units per second, but it's also possible that it's a variable function and it's just on this interval that it's 4 units per second. All right, so there's a lot of different possibilities, but bottom line is we're going to take the derivative of this. So 2 parentheses, it's classic chain rule, x minus 3, the quantity squared. Then we take the derivative of the inner function. The derivative of the -3, that's going to go away because derivative of -3 is equal to 0. But the derivative of the x, that's with respect to time. So I need to multiply this by the derivative with respect to time of x minus 3, which in turn becomes dx dt minus the derivative of 3 with respect to time. Well, derivative of a constant goes to 0. So it's only the variable component that I care about giving us the dx dt. All right. So that makes things a little cleaner, easy to substitute in, but there's also a lot going on there. Why is it? Oh, Lord only knows why it's to the second power. There's no valid reason why I make some of the mistakes I do, except to say it's almost 7 o'clock on a Tuesday evening, and sometimes the brain cramps. Yeah, shouldn't have been to the second power. Apologies. All right. So now we go plugging and chugging away. They told us at the moment that x is equal to 1, so 2 times 1 minus 3. They told us the x coordinate is increasing at a rate of 4 units per second, right? So that's saying the x coordinates rate of change, dx dt, is 4 units per second, right? So my dx dt gets replaced with a 4. So 2 times -2 times 4 is going to be -16, right? But we can't just leave it unitless, right? We got to throw in the appropriate units. Now, it does make sense that if x is measured in just simple units, so would y, but you could also play it by the computations here, right? So dx dt is measured in units per second, right? X itself is measured in units. Dx dt is measured in units per second, right? So you can go that route. Lost my place here for a second. So, yeah, I don't know. Like, there's no easy way to tuck that in. So I would just kind of, maybe I'll just do it this way. We'll do it like this. And then seconds. Yeah. All right. And then, you could just kind of reason it out that way. So units per second. You could also look at the relationship based off of, any kind of phrasing in the question. Sometimes it'll say, specifically what the units are measured in terms of, but if it doesn't say that, then you can pull it from the rate that's given to you, or you could pull it from the context of the problem. Right? So, yeah. And I mean, the -16, the 16 itself, I don't know. Could be right, could be wrong. I know it's right because I've been doing this problem for like 25 years. But like, there's nothing about the 16 that stands out to me and screams, oh, this must be the right answer. It's the negative that I really care about, because I know that this point is going downhill. All right. As I work my way in increasing a value, so from left to right, this point is going downhill over that interval. So it should give a negative for the y value, positive for the x value because it's going to the right. So negative y divided by positive x would give us a negative y over x, right? So it should give a negative result. The 16, could be a mistake. It's not, but it could be. You never know. So you got to double check that part of it. But, the negative is really, you're on the right track at a minimum if you have the appropriate sign. Now, the second part can be a little on the funkier side, because it says at the moment x is equal to 1, how fast is the point's distance from the origin change? That's a fun one. So let me show you what that looks like graphically, and then you'll get a better idea what's going on. Because you go back to step 1 here, draw a diagram. How do you draw a diagram in motion? It was bad enough you saw me scrambling around trying to draw a sphere and a cube, and it doesn't even look like a cube. Right? But to get a point to move along a curve in a way that's actually meaningful without actually animating it, it's not practical, right? At least on paper. So technology is encouraged. Regardless, if you want to create a line segment, I think the easiest way to do that is to create a table of values in Desmos, connecting the 2 points that you're interested in. Right? So hit the little plus sign, select table. We want to connect it to the origin 0, 0. Right? So that's 1 point. The other point is the moving point. Right? That's this one. I define that here as a comma f of a. So put my second point in the table as a comma, f of a. Desmos will understand. It knows what you're trying to say. Right now, at first glance, it's like, well, what did we accomplish? It just plotted 2 points, right? First thing, I mean, I could get rid of this now. I don't need it because I have something that'll actually plot the point for me. It's in the table. If you long press on the scatter plot here, I hate how it does that. I don't know why. It's so aggravating. So long press on the scatter plot. You see an option for a line. Just ignore that shading. I don't know why. If you select that, it'll connect the points using a variety of different line types, whether it's a dashed or a dotted line or just a plain old good old fashioned solid line. You can make it thicker, you can make it thinner, you can change the color. Right? The color here is fine because it's distinct enough. But now, when I animate, stop moving. Oh, dang it. When I animate my A, you can see that a line, or the line connecting A and the origin, is changing to accommodate the change in position of A along the curve. So we have this distance corresponding to the position of A. It's clearly changing depending on the moment in time. It's just a question of, all right, well, how fast is it changing? Specifically at the moment that x is equal to 1. Right? It's a linear distance, so we're expecting an answer that's going to be in units per second. So you can also keep that kind of thing in mind as you go into a problem, rather than waiting for, all the calculus to shake out. But we need a measure to represent distance, right? Fortunately, we have a couple of ways to measure the distance between 2 points on a line, or 2 points on a line segment. And that would be either the Pythagorean theorem or the Pythagorean theorem's less attractive cousin, the distance formula, right? So a squared plus b squared is equal to c squared. The distance formula it's not pretty, but it works by points, so you might find that to be a little bit more appealing. Now I'm going to freeze this at a particular moment, maybe not that moment. Let me get a better moment in time. Just freeze it right there. The C value would be the length of the line segment that we're interested in. Right? So that would be pretty good. So I could say C squared is equal to A squared plus B squared. Now it seems like, oh, well, why would I write it that way? Well, the C squared is the function itself. Right? That's going to be dependent on 2 components, the X component and the Y component. Right? Or the horizontal and the vertical components, the A and the B. All right. So if I need to figure out a location along a graph, and I'm going to go a little crazy with Desmos here, just so you can kind of get the visual, but I'm going to make another table, 0, 0, and go to A0, just to show you another line segment. All right. So that would be the length of side A, for example, or it could be B, it doesn't matter, they're interchangeable. Then I can also do another table going from A0 up to the point on the curve we established before was A comma F of A. So A F of A. All right, and again, put a line there. Maybe I'll make it all black so it's a little distinct. I don't know why it does that. All right, there we go. So now if I move it, the triangle changes along with it. And so you have that nice Pythagorean relationship. I can kind of zoom it out. It looks a little bit better. All right. Obviously not something you need to do, but it's good to create a nice visual, because, I mean, am I going to ask you this exact question on the test? Absolutely not. but can I ask you one that involves, instead of x minus 3 squared, can I ask you something, same structure, but a cubic function, or even maybe a trig function, something where it's just the y equals that's different? Sure, absolutely. All right, so what we would look at when it comes to this figure, now I can actually just kind of bring it in, mark it up a little bit. I just got to remember to save these diagrams, these links. Actually, I'll take that as a typo. So the typo should be, it's not really a typo, but link the Desmos to this question. I'm creating a Desmos right now. Like for future semesters, it would be really cool if the students can click on the link and then bring them right to the Desmos without wasting time in class to actually click on it. And so we have an x here, an x distance, and a y distance. All right. Every coordinated space is x comma y. So that should make sense. All right. So using Pythagorean theorem, we would say x squared plus y squared is equal to, we could still call this c. There's nothing wrong with that. So we could say c squared is equal to x squared plus y squared. All right. And you're like, all right, cool, congratulations, it's awesome. Yay. But it's actually really helpful because we can now look at this and say, all right, hold on. We know what y is. They told us up here. Y is x minus 3 squared. That's a given relationship. All right. So x squared plus x minus 3 squared. Right? Because the Pythagorean theorem has a power of 2 in it, but so did the original function. That looks kind of intimidating, but it's really not that bad because you raise it power to a power, you just multiply the powers. So x squared plus x minus 3 to the 4th. And now, with chain rule, that's not too bad because it's like little baby chain rule. It's not even like the hard chain rule type question. Right? So that's what c squared would be equal to. Right? So what we would want to do at this point, again, is determine what the rate of change is of c, right? So how fast is the point's distance from the origin changing? So what is the rate of change of c per unit of change in time? So dc dt, right? So I have a function that relates c and everything else. I have to differentiate it. Now there's 2 ways to differentiate it. One, I could take the square root of everything so that c equals, make it a little bit cleaner on one side and make it hideous on the other. Or I can accept a little bit of ugliness on the left for a lot more cleanliness on the right. Right? So I'm going to differentiate this function of x as is by taking the derivative of both sides with respect to time, d dt, not what I meant to do. So I'm going to differentiate these 2 sides of the equation with respect to time. On the left-hand side, and again, every dimension of this triangle, I can hit animate again, every dimension of this triangle changes depending on time. There's nothing that remains fixed, nothing that remains constant. So every one of these variables, x, y, and c, are functions of time. Now, in this case, I only care about x and c, but I have to keep that in mind. I got to know what are variables and what are constants. It becomes more and more important as time goes on. Right? Pun intended, I guess. I don't know. So c squared becomes 2c, but then the derivative of my inner function, c prime or dc dt. The addition rule for derivatives tells me that I can take the derivative of this and the derivative of this separately from one another. Right, so 2x, x itself is a function of time, so times dx dt, or x prime if you want. The derivative of x minus 3 to the fourth would be 4 parentheses x minus 3 to the third power. The derivative of the inner function, x minus 3. We talked about this before, but we address it again very quickly. X minus 3 has a derivative that would be 1 under normal circumstances, but because x itself is a function of time, we then have to multiply by that inner function's derivative, or derivative of x with respect to time would be x prime or dx dt. So we're going to get another dx dt here. All right. Now, they told us in the open that dx dt was equal to 4, a positive 4. They told us in this problem that x is equal to 1. We have a built-in 2 here, so 2 times 1 times 4 plus 4 times 1 minus 3 cubed times another 4. On the left-hand side, we have a 2, an unknown c. We haven't figured that out yet. And we're looking for dc dt. All right, that's c. Yeah, we don't know it, but we can figure it out. Right? And that's because at 1, yeah, I got it labeled right here. At the x value of 1, the y value is equal to 4. Right? So at this location, we have coordinates of 1, 4. So if I let my animation go over here, eventually, one leg of the triangle is going to have a length of 1. The other leg is going to have a length of 4. That's the same as saying 1 squared plus 4 squared is equal to c squared. 1 plus 16, 17 is equal to c squared. Pythagorean theorem tells us that the square root of 17 is equal to c. All right, so I could pop that in over here. And that's just a quick side calculation. That's in lieu of actually taking, I mean, we could have taken the square root of this whole thing over here, but just think about how disastrous that would have been. You'd have a chain rule with chain rule inside the chain rule. It would have been a nightmare, right? And this wasn't too pretty to begin with, but the alternative would have been too ghastly to consider. So we have 8. We got negative 2 cubed is going to be a negative 8 times 4 is negative 32 times another 4. It's going to be negative 128. All right. So then 8 plus negative 128 is negative 120. 2 radical 17 dc dt. Divide dc dt. We knew going in that it was going to be linear units. So when I divide by 2, I get negative 60. When I divide by the rad 17, I'm stuck with the rad 17. The linear units are units. and the reference to time is in seconds. All right. Always possible there's a computational error in there. I hope there isn't, but that's why we check our work. The negative makes sense because as we go from left to right, that hypotenuse is getting shorter and shorter until we get to a certain location, and then it starts getting longer and longer again. Right? So it makes sense. It's not talking about direction, it's talking about size and how fast is the size changing. That hypotenuse has a size to it. And as it moves down the curve here, that size is getting shorter and shorter. So that would have a negative derivative. It gets longer and longer over here, so it would have a positive derivative, right? So these are things that we want to start trying to make sense of as we go forward. And I think things like Desmos kind of help do that. All right, so I'll save this, this Desmos calculator and get it linked up so that you have access to it. Because honestly, if I did it right, and I think I did, let me just double check real quick. Let's say I make this cubed. Yeah, it should work no matter what the function is. Yeah. So any question that asks you to find the distance between a point on the curve and the origin, you'd have the means to do that. And also you could even modify this to get a separate point in space, because all you'd have to do is change any 0, 0 to, let's say you wanted to find the distance between 1, 0. Just change all your 0, 0s to 1, 0s and you're good. So there's a good way to get visuals out of this. All right, so I'll get this linked up for you so you have it. But I think it's pretty reasonable. Reasonable was not the right word. Sometimes words just come out of my mouth. I apologize. Useful is the word I should have used. All right, so we'll call this distance from origin to curve. I don't know. I'll come up with a better title later. I just don't want to lose it. All right. Next one's a fun one, but it's so very similar to B here, even though it doesn't seem like it at first. That I would just be kind of rehashing the same problem again. So I'll put a star on that one and we'll tackle that in next class. I wanted to get into one where we talk about, the cone. Yeah, so I'm going to put a star on the next one, number 5, which is also, it's also a triangular situation. It's a little trickier, but still very manageable. I wanted to tackle number 6 with you though. Yeah, this is a fun one. It's classic. I mean, every version of a calculus textbook has this kind of question in it somewhere, because for whatever reason, we're all very concerned with inverted circular cones. I don't know why. I think I do. I think somewhere along the lines, somebody was drinking out of a water cooler, the old school ones where right next to it, they had the little paper cone shaped cups, and they were drinking out of it and they were enjoying their cool, refreshing water. And they noticed that water was dripping out of the bottom of it. It was just kind of dripping out of the bottom. And they were like, oh, I can make a math problem out of this. I mean, it might sound lame, but everywhere I go, I look at things and I say, oh, I can make a math problem out of that. And then I do, and then it ends up not working out very well. But my mind always works that way. So I'm guessing somewhere along the line, somebody did something like this, like cylinders. Like they always talk about silos because somebody, in agriculture was like, all right, how much grain can we fit in this bad boy? And then they're like, all right, let's do some calculus. And here we are, so, but this is an interesting problem because one, I can draw a cone and I'm very thrilled about that, a right circular one. I mean, it looks glorious. I mean, you saw this cube here. I can barely handle a cube, but for whatever reason, I can make a cone all day long, even without the app. It's astonishing. I don't even know why. Water tank has the shape of an inverted circular cone with the base radius, right? So the circular part, that shaded part at the top, that would be the base, because this one's inverted, right? So it's not actually sitting on its base, but it's saying its base radius is equal to 2 meters. Right, so it's a big one. It's a big inverted circular cone, right circular cone. If water is being pumped into the tank at a rate of 2 cubic meters per minute, so that's another measure of volume. So that's a dVdt. Find the rate at which the water level is rising when the water is 3 meters deep. Right. So what we need to do is just kind of imagine that water is rising through this inverted circular cone. But let's not imagine too much. I'll try to draw it. Something about concentric circles that are really. Right. So here's the water level. Right. Pretend that this is all water. I haven't figured out that part of it yet. All water. Looks all right, I guess. So water's being pumped into the tank. So somebody's, pouring water in. I don't know what it looks like to pour water in, but there you go. Water's going in. It's filling up. Splashing, yay, okay. All right, that's enough of that. All right, so it's filling up. We want to know how fast that water level is rising, right? The water level will be 3 meters deep at some point. We want to know how fast it's increasing, because we know that the water level is increasing. It's like a scene out of, well, any movie where there's a sinking ship, but like, I'm just thinking of Justice League, the crappy one. Well, they were both crappy, but the really crappy one. At the end, 3/4 of the way through, they're underneath Gotham Harbor. What are we under? Gotham Harbor. Oh no, we're scared. And so the water's filling up, and it's coming up the tube, and they're all going to die. But then they didn't really explain how they survived. But you've all seen the movies like that. I'm going to go with, you know what? I'm going to do it. I'm going to go with Batman as the word of the day. It's not really like a word in the classic sense, proper name, but Batman, like the fictional character Batman and Robin kind of Batman. All right, so there you go. That's the word of the day. All right. So this water level is rising. There will come a moment in time when it reaches a height of 3 meters. All right. The overall height of this inverted circular cone is 4 meters. So it's almost there, actually. All right. So the whole thing is 4 meters. But the water level is only going to get up to 3 meters. All right. So this measurement is going to be 3. The whole measurement, and it's kind of hard to draw the 4 in there without it being too messy, so I'm not going to. But the whole distance from point down here to the base on the top, that whole distance is 4 meters. It's not going to be in proportion, or visually anyway. So we want to know how fast that water level is rising. Well, we do know a couple of things. One would be the volume of a cone. Right? Maybe you don't know that formula, but you know one exists. All right. So volume 1/3 pi r squared. All right. It's actually kind of an exercise in mathematics geometry to show that that 1/3 of the volume of a cylinder actually would end up being a cone. It's like, how does that work? You know, it's kind of cool. Right. So I'm looking forward to it. Let's put it that way. I'm looking forward to the movie. It's been about time since we've had a win in the DC universe, like a real win. Yeah. So volume is 1/3 pi r squared. I could take the derivative of this, but the problem is, if I take the derivative, 1/3 pi r squared, geez, h, 1/3 pi r squared h. All right. The problem that I have here is that they gave us lots of references to height or depth, but they didn't give us anything about a rate of change involving the radius. Now we do know that the radius will have a rate of change, but we don't know what that rate of change is, right? Because it says find the rate at which the water level is rising. Right. So right here, find the rate at which the water level is rising. That's saying dH dt. Now, just understand, we use height and depth interchangeably, right? When we say height, we can also mean depth, so the formulas work the same way, all right? So, but I don't have a dr dt, nor do I want a dr dt. If I were to take the derivative of this formula in its current form, it would create a dr dt, and I don't have information to evaluate that. So I need another equation, right? Secondary equation needed. So if we take this cone and just kind of chop off part of it, right? If we chop out a quarter of it and just look at the cross sections, right? Now that's something I don't have a chance in hell of being able to draw effectively, but what we would be saying is we'd want to get rid of all of this. Just kind of chop all this out and just look at the cross section, right? So this is pretty awful, but you're just carving out a quarter of this cone. It's a question of, well, what would you see if you did that? Well, what you would see would be two overlapping triangles, and they would actually be right triangles. If I could actually draw a right triangle. Oh, Lord have mercy. Okay. That's how you know class is coming to an end. Because come on, link up. There it is. All right. So you would end up with a figure that looks something like this. With the 2 on the top, 2 meters. This whole length here would be 4 meters. They told us that up here, 2 meters and a height of 4 meters. Now, the inner triangle, this piece here, this has a variable height and a variable radius. It all depends on the moment in time. Can't make a squiggly bracket now. All right. It just so happens that we care about it when the height is 3 meters, but it's not always going to be 3 meters. It's only going to be 3 meters at a particular moment in time. The relationship here is that the ratio of R to 2 will be the same as the ratio of H to 4, right? So the question is, can we just do the Pythagorean theorem for the base and the height, as the slope of the C would be the rate of change of the radius? Well, the thing is, the C value would represent, I'll show you, C would be this side, and we have no information whatsoever about the length of this side. We don't know the rate of change, and we don't know any distances. I mean, we could figure out the distances. That part would be easy enough, but we don't know anything about rates of change. And so if we solved using the Pythagorean theorem and made a substitution there, then we would be introducing another variable that we don't know anything about the rates. Because it's not about the actual length, you know, because we know radius lengths and we could figure out radius lengths. We don't know the rate of change of radius, which is why the R in this equation has to go, right? So that's the key little bit to understand here. You kind of look at it like, all right, we read the problem, we take a look at what we have here in terms of the d whatever dt's, right? I have a dv/dt that was given, and I'm looking for a dh/dt. What that tells me is that there should only be two variables in my original equation, the one that I'm looking to take the derivative of. Those two variables should be v and h, nothing else. So I have a formula for a volume of a cone, but that formula has an R in it. I look at that R and I say, well, if this is going to work, that R has to go, right? So that's why we ended up down this path. That's a good question and a good point, right? But what we're able to do here now is solve for R. So R is equal to 2h over 4, which in turn becomes h over 2, or 1/2 h. So now I can replace the R with a 1/2 h. Little simplifying goes a long way. So 1/3 pi times 1/4 h squared times h. So we're looking at, we put our multiples together, or constant multiples, pi over 12 h cubed. All right, much simpler formula. All right, now we haven't taken a derivative yet. That's the next step. We're going to take the derivative d dt of both sides of this equation. A little shorthand notation for you. All right, so dv dt would be equal to, we're taking the derivative of this side with respect to time. So 3 times pi over 12 would be 3 pi over 12, simplifies to pi over 4. H squared, and again, h is a function of time, so multiplied by h prime or dh dt. They told us indirectly that dv dt was equal to a positive 2 meters cubed per minute. I say indirectly related to the positive part because the water is being pumped into the tank, which means the water level is rising, the volume is increasing. All right. So 2 is equal to pi over 4 h. They told us take note of when h is equal to 3. So 3 squared times dh dt. So 2 would be equal to 9 pi over 4 times dh dt. Divide both sides by 9 pi over 4, or multiply both sides by 4 over 9 pi, and you get dh dt is equal to 8 over 9 pi. Okay, and the units of measure here, well, h is a height measured in meters, so meters. Time, t is time measured in minutes, so meters per minute. So 8 over 9 pi meters per minute is what we would get as a result. All right, but you can see here that this is a little bit of a twist where, I mean, aside from the fact that you're dealing with a three-dimensional figure, but we've handled those before, you now have a need for a second equation. All right. So I know that there's a mixed problem set that follows. Some of them are a little crazy. The only ones that I really want you to focus on are the ones that I had you star. Those are the really important ones. So give those a shot, and then we'll kind of handpick some of the because there's a bunch. You know, we don't need to do them all, but we should do. There's a couple in there that we're definitely going to want to do together, but we'll do those next class. All right. So let me stop the recording.